We have a lot to cover today. We need to finish up stereochemistry. We need to start alkynes. Chemistry of alkynes was a handout that was sent to you by email. This is a yellow sheet here. We finished up compounds up there, diastereomers. Those two examples there. I sent you an email. We did not mention the terminology. Actually it's rethrow and 3O. What is a rethrow and 3O? Rethrow and 3O is terminology used to describe Fischer projection when you have the high priority groups on the same side. That is a rethrow. When the high priority groups on opposite sides is 3O. Okay, remember those with capital E. Draw capital E. All the lines are to the same side of the vertical. A rethrow. Draw capital T, you have a line on that side and that side of the vertical for your T. So you have both sides. Or we can say opposite sides. And so in some of those up there that we drew, you can look at them and label them as a rethrow or 3O. That's a diastereomeric term. Used there. Let me show you. I can get the two right handouts in my hand. We have a yellow one and a white one, In the white one, we'll do some of those on the first page. If you turn back to the last page, you'll see your carbohydrates. When you get to biochem, you'll learn your carbohydrates like this, including glucose. These are typically shown in Fischer projections. Your 6-carbon carbohydrates have 4 chiral carbons. And so they have 4 crosshairs, boom, boom, boom. And you could, if needed, determine RS for each one. First off, it says in the notes somewhere that there's a difference between capital DL and little dl. Little dl refers to if it rotates light left to right. Capital DL means something different. When you get to biochem, you'll learn that. It's also written somewhere in the notes. I'm not going to take time now. For example, all of these are called D. That's because they all come from D-glyceraldehyde, essentially, where in terms of rotating PP light, some of these are D and some of these are L. Okay? We want to use little d, little l in this course, for what we're doing. You look at these are all stereoisomers. They all have the same connectivity. You've got an aldehyde group up here and a CH2OH down here. Every carbon has an HOH, but they're different orientation or configurations. This is chiral because there's no plane of symmetry. You cannot cut right through here because you have aldehyde on top but not on bottom. And then you can't cut right through here, obviously, because you have OHs on one side and not on the other. Fischer is very easy to see planes of symmetry. You can trust that, either vertical or horizontal. Mirror image of this would have OHs all on this side. None of those are that. None of those are the mirror image. None of those are the enantiomers. What's these are stereoisomers. Hope you all agree with that. What's the relationship between the two? If you look at the flow chart on like the second page, there's only 2 types of stereoisomers: enantiomers or diastereomers. Enantiomers are mirror image. Those are obviously not mirror images. Thus, they're by default diastereomers. Diastereomers have different physical properties. Diastereomers can thus be separated potentially. I mean, mean, they're going to be very similar. They're both quite polar, but they can potentially be separated. There's a specific type of, more specific type of diastereomer called an epimer. An epimer is when you have multiple chiral carbons and there's only one of them has been switched. For example, look at these two, allose and altros. What's the difference?
First.
Only that top carbon called C2. The only thing that's been switched. Whatever this is, RS, that's been switched. Because only one thing has been switched, we can also call that an epimer. Epimer is just a specific type of diastereomer. I mean, if we look at this versus, is allose and glucose epimers? No. Yeah, that's carbon 1, 2, 3. These two are called C3 epimers because at C3 it's been switched or epimerized. Are these two epimers? No. How many things have been switched? So they're not epimers. Epimers are only one thing has been switched. But these are diastereomers, right? Because they are stereoisomers, but they're not mirror images. So all epimers are diastereomers, but all diastereomers, right? Okay, so that's that. By the way, erythro and trio comes from these two 4-carbon sugars here. Erythros, guess what? The two OHs are on the same side when typically drawn like this. That's where erythro comes from. And in threos, the two high priority groups are on opposite sides. And so we can call that, refer to other things like that as threo. Let's see here. Okay, we did number of chiral carbons. Maximum number is what? N, 2 to the N, with N is number of stereogenic centers, stereogenic sites. How many stereoisomers possible for this compound? Glaucoma drug. Stereoisomers possible. 5. Well, how many stereogenic centers? I see a chiral carbon here. Here, 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 here. There's 5 chiral carbons. I bet agree they're chiral. What else do you see that's a stereogenic center?
Double bond.
There's 2 of them.
That's a stereogenic center.
Is that double bond stereogenic? Does it have potential for stereochemistry?
Yes.
Can it be cis or trans?
Yeah.
Sure, it's drawn as trans here, but could it also be cis? Sure. So we can star that whole thing. The whole thing is 1. What about that? It's drawn there as cis. Could it be trans?
Yes.
It could be. Any others? Can that double bond be,
No.
right there it's cis, can that be trans?
No.
Not in a 6-membered ring. 5 and 6-membered ring double bonds cannot be turned trans. Huge rings, yes. I'm not going to give you a huge ring and ask you to decide how big it needs to be. Typically 5 and 6 can't be. So these double bonds are not stereogenic. You can't show that. It can't physically exist. That's it. How many we got? 6. What's that, 7? 2 to the 7 is 128. Okay, so draw them all. Okay? What would you do? Well, you just draw all the different, you can make that trans, that cis, make that R. That'd be one. As drawn, it's generic here. Okay, this is generic. And you can draw all bonds bolded, whatever. Okay, but if you sat down and did it this weekend, all 128. Now, could any of those be meso? Meso got an internal mirror plane. I mean, can you imagine any internal mirroring of this? No, I mean, you'd have to have another one of these here. I mean, I don't think any of those are meso. I think the answer is 128. I don't see any meso possibility there. Diastereomers, epimers. I think at the bottom, I think we've already pretty much covered. What's the enantiomer of a compound that's RRSR if it had 4 carbons? SSRS? Because when that looks in the mirror, what does it see? Everything's switched. So if you had the same compound, well, there's the answer. If you had the same compound and it was SSRR, what would be the relationship between these two? It'd be diastereomers. That's not the mirror image. And more than one thing is switched, so you wouldn't call it epimers. Okay? I think we pretty much already covered that. The back meso compound, we've already covered that. Plane of symmetry. Even though it has chiral carbons, it still has a plane of symmetry. We'll do some examples. Okay, 7 and E. Let's go to the warm-up page and let's do a few examples here. Any particular one at the top you want to do?
You the one with the Fisher projection on the left? That one?
Which one? This one? Fisher projection? Is it a rethrow or a 3O? Okay, with phenyl at top, ethyl at bottom. Phenyl at top. There's the phenyl. There's the ethyl. It says put the phenyl at top. Ultimately, I'm going to draw it with. What do I got here? There's the ethyl. There's the phenyl. I got 2 chiral carbons here. So I got 2 crosshairs with phenyl at top, ethyl at bottom. So that's just ethyl, CH2, I can just draw it like that. That's 2 H's there. Here was our chiral carbons. Ultimately, we want to have it here. Okay, phenyl at top. Since phenyl's at top, ethyl's at the bottom, is the ground over here or over here? Ground is over here. So ethyl is closer to the ground. I want to stand on the ground. I'm going to look through here, looking away. Okay, pretend I'm up there looking away. See, if I'm looking away, the chlorine is going away from me. See how the chlorine is going away from my little guy right there? With the chlorine going away, if I'm hovering up here, looking down there, the chlorine's going away from me. What side is the phenyl on?
To the right.
On the right, because it's coming out of the board. Here I am, hovering up here. If I agree the phenyl is coming out of the board, that's what that bulb means? If I'm hovering up here, the chlorine's going away, and the phenyl's coming this way, and I'm looking down, the phenyl's going to the right. So, with the chlorine going away, phenyl's on the right. What's on this carbon going back? Yeah. See, it's going behind the board. If I'm looking down, that H is going back. That's my left. It's on the left. Now the ethyl's in the plane. So I'm going to look at it, keep the feet on the ground. I'm going to look at it through there. Now I can lay right here, but the ethyl, that bond right there is important. It's going away. With this going away, this fluorine is which way? coming towards you guys, so it's on my left. With the alpha going away from me, it's on the left. The alpha going away, that's what that means at the bottom. Fluorine's on the left. That means the undrawn H there is on the right. Here's the compound as I see it. I'm asked to draw the phenyl at the top. That was at the bottom already. Okay, here, I told you this by email. These top three can just be rotated, like this. We can put the phenyl up here, the chlorine here, and the H moves over there. When we do that, the phenyl goes up. What moves over here? And the H moves over here. F is here. H is here. This is it with the phenyl at the top, ethyl at the bottom. When drawn like this, is it a retro or a 3O? On this carbon, chlorine is high priority. On this carbon, fluorine is high priority. What is it? It's a retro. Let's see if we can put this on the board here. Let's go back to this compound here. Pretend that's a phenyl there on that end. This is in the plane, but the phenyl is coming forward, right? So this is sort of this here. Chlorine's coming straight down. I'm going to make chlorine green. See how it's coming straight down in the plane? And then the fluorine is red, it's coming out. So I'm going to put it here. Pretend there's a phenyl here. There's the compound on the board as originally drawn. Does everybody sort of agree? Okay. I want to draw it with the phenyl. No, I drew this with the chlorine going away. So I looked up there. So I come up here looking down. I'm just going to get up here. Instead of doing it like this, I'm going to here. Okay, you see the chlorine going away from me? It's green going away. With it going away, the phenyl is to my right. You see? I'll just turn. Chlorine going away, phenyl to the right. Chlorine going away, phenyl to the right. This little H is over here to the left. Okay? Now I look down here. Kept my feet on the ground. The feet are this way. And I said the ethyl is going away. With the ethyl going away, you see how that's going away from me? It doesn't matter what that's doing. That bond's going away. With it going away, I'm just going to bring it down. With it going away, this fluorine is on my left. You see? The ethyl going away, fluorine's on the left, H is on the right. That's that. Now if I wanted to turn it, that's the bottom here. Fluorine over here, H over there. This is going back. Down means it's going back. Now up here, if I go back to original view, I would turn it. Chlorine going back. Yeah, like that. There that is on the board. Chlorine going back. H is over here. Phenyl is over there. Now, if I want the phenyl to go back, because that means it's going back, I can just turn this and make it go back. And when I make it go back, where does the chlorine swing around? It's now on the same side as the F. See, these top three here can just spin like this. That is, if you want the chlorine going back, the phenyl is going to be on the right. But if you want the phenyl going back, the chlorine is now on the left. What if you want the H going back? well, then the chlorine's going to be on the right. Because, see, I can just put the H here, the chlorine will move over here. So these three can just spin sort of like this, with this bond not spinning. It's very common to draw it and spin it the way you're asked to show it. Questions about any of that? So ultimately, we got erythro and not rheo.
Question. So if you drew the chlorine and the fluorine on the opposite side, it would be an enantiomer, and thus be wrong for this question.
Right. If the final answer had chlorine here and fluorine here, it would still be erythro, but you would have the enantiomer. It would not be that. You would have drawn the mirror image, and it would be wrong. The mirror image of erythro is erythro.
Yeah.
You would have drawn the enantiomer. Is this compound chiral? Yes. It's got two chiral carbons. Does it have a plane of symmetry, though? No, I don't see a plane of symmetry. That's certainly not a plane of symmetry. And that's not a plane of symmetry. Trust your two planes and your fissures. Vertical and horizontal, if you don't see symmetry, then it's not there. That's another power of the fissure. Easier to see planes of symmetry, etc. RS over here. Anybody got it?
Yes.
Yes. Okay, H is not forward or back. So how are we going to do this? We have to look at this with H back. I have to stand over here and look through there. What do I see? I'm going to draw a fissure. I'm looking through there. Bromine's coming towards you guys. SH is going back. F is going straight up. What's going straight down as I look through there? H. So I look through there. What's on my left? Bromine. And that's what's on the right going behind the wall. SH. Now this is easier because now we know what this H is doing. Priorities would be bromine. What's next? S or no? S. F. Counterclockwise. How's the H now? H is back. Counterclockwise. So what is this? S. If H is in the plane, you got to look at it differently, and I would recommend drawing it differently, drawing it in a fissure, then do it. How might you separate the two enantiomers of this compound? Right here we have R and S. We could have racemic mixture. How would you separate those two? Enantiomers have same physical properties, except for rotating pp light. One of the most common ways is to, if you can make a salt of a compound. If you can make a diastereomeric salt. Diastereomers have different physical properties. They can potentially be separated. So you have to go back to how do you make salts? Well, what type of functional group do we have in this compound? Carboxylic acid. What do you want to react it with to make a salt? A base. Now let's say we have R and S here. 50-50 mix. Or 60-40, whatever. We got R and S. Let's react that with, I'll give you some random example. How about this here? How about that? 6-membered ring, saturated nitrogen, propyl group. Chiral carbon. Is it R or S? Nitrogen 1. Carbon, carbon, carbon versus carbon, 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 carbon. I think this is going to be 2, 1, 2, 3. H is in the back. This looks like R. Okay. Correct that with this. By the way, this is the major constituent of hemlock. Who drank hemlock?
Socrates.
Socrates, that's the main poison of hemlock. Conine. Comes in R. Now, so I drew R here. Well, these two react to form a salt. That's an acid. What do we know about sp3 nitrogens? They're basic. This will take the H, and you'll get, I'll just draw it down here. You'll get the, look at that minus, and you'll get, nitrogen will take an H, that'll become plus. You'll have this here. This is your ion pair after your acid-base reaction. These electrons take the H, electrons stay behind. You make this ion pair or salt. But there would be two scenarios here. You can have R, all this is R, plus what? You'll also have some that are S/R. You'll have RR salt and you'll have SR salt. Because the original was, some was R or some was S. The R will react with the R to make that salt. S will react with the R to make this salt. Now you have RR versus SR. What's the relationship between your two salts? Apomers, or more broadly, diastereomeric salts. Okay? Ion pairs are treated like one compound. I mean, if these were bonded, you would say, well, this is RR and that's SR. They're bonded just ionically. Not really a bond. These can be separated at this point as a salt because they have different physical properties. Then to get this back to the OH form, you just add a strong acid and this will become protonated after you separate. Basically, all that's described on the very back. Okay? I know some of you have already been looking at that. Don't have a lot of time to go into that, but that's separation of an enantiomer using, in this case, this base would be called a chiral resolving agent. To make diastereomeric salts. Now, these may not always separate. These may be very difficult to separate. But in some cases, they may readily separate. You can read some examples of how they do that. In terms of separation, maybe you try to recrystallize, and maybe this one crystallizes and this one stays dissolved. Or maybe that one crystallizes. Or maybe nothing crystallizes and you can't separate them. Diastereomers are potentially separatable. So that's the idea of that. And that's what I'm talking about with G there. Okay, big D, big L on the bottom, we mentioned that. Let's do some of these here. Identify the following as chiral, achiral, or meso. Let's do this one first. Ultimately, if you're saying it's something chiral, ultimately you want to say, is there a plane of symmetry? If it has a plane of symmetry, it's not chiral. Do you see a plane of symmetry here?
Yes.
Yeah, boom. Plane of symmetry. Top half is mirroring the bottom half. Thus, that compound is not chiral. That would be achiral. Okay, let's go back over here. Does this one have that same plane of symmetry?
No.
No. Forward bromine is not being mirrored by forward bromine. There's actually no plane of symmetry there. There's not one there, and there's obviously not one here. Now it has two chiral carbons, no plane of symmetry. This is chiral. What does that mean to us? The mirror image is going to be different. Like your hands, the mirror image is different. Will the mirror image of this be different? Mirror image is the same thing. That's what achiral means. Now this has two chiral carbons. That is chiral and that is chiral. Those are chiral carbons, but as a whole, the molecule is not chiral. How about this?
So is that
Thank you. It's achiral, but what does meso mean? Meso is a special case. Yeah, this is actually called meso. It's achiral. What's the difference? Meso is used whenever you have chiral carbons, yet the molecule as a whole is not chiral. And so that's actually would be better to be called meso. Okay. Meso means, hey, it does have chiral carbons, but it's not. How about this? That's not a plane of symmetry because chlorine's not mirroring bromine, no other, so this is chiral. Okay? Those three we're going to have to do Fisher. These acyclic ones, it's best to draw a Fisher projection. Before we do those, let's try these over here. Others with rings. Basically, what are we doing? We're trying to find Waldo. That is, we're trying to find a plane of symmetry. Do you see one here?
You can go diagonally through them.
Is that a plane of symmetry? Half a chlorine coming forward, mirroring a half a chlorine coming forward. Half a ring, mirroring half a ring. Half a bromine going back, mirroring a half a bromine going back. That is indeed a plane of symmetry. What do you want to call this compound?
No, meso.
Why achiral and not meso? There is a plane. Is that chiral? You go that way and you get the same as this. Those carbons are not even chiral. No chiral carbons. I'd call this achiral. What about this? Do you see a plane of symmetry? I mean, obviously that's not. You got to have a bromine over here. Is that a plane of symmetry? No. I see no plane of symmetry. That means the mirror image is going to be different. This is chiral. Now this is chiral. You got a methyl, an H. This way you get a bromine, that way you do not. That's chiral. That's chiral. It's three chiral carbons. How about here? I see two planes of symmetry. That's a plane of symmetry. And you also have one right through there. That's not even chiral. It's got a methyl and H. This way is the same as that way. It doesn't even have chiral carbons. How about this guy? That's not a plane because you need a bromine there. But that is. Methyl coming out, mirroring methyl coming out. Half a bromine going back, mirroring half a bromine going back. That's chiral. That's chiral. That's not. You got chiral carbons, yet as a whole it's not chiral. What do you want to call this? Yeah, that's classical meso. How about these guys over here? Plane of symmetry is right through there. If I redraw this, if I redraw it like that, you can easily see the plane of symmetry coming through one point and going between the other two carbons. This is where it's just turned a little bit and the point is over that way. Can you imagine coming through there? I just take this and sort of turn it a little bit, and then it's like that. This is another way to sort of show this, you know, kind of straight up. Sort of like the ring is flat, with the bromine either up or down. And you'll see that at all? Oh, there's that plane there, and it's just turned a little bit. You have to just imagine splitting right between the two bromines, right between that bond, and going back right up to that point. That is chiral, so it's meso. You got two chiral carbons, yet as a whole.
How are they chiral? Because it looks like they're going through the same. Oh, never mind. I see it.
Bromine H, yeah. That way you get a CH2, this way you get a CBr. That's chiral, that's chiral.
Okay, I got you.
How about over here? Well, that is not there because if you turn this, it'd be like it's not. This would have to be up to be a plane. If that was up, do you see the plane there? With it down, it's not. There's no plane here, so this is chiral. So these are some examples of different ways compounds may be shown, and you have to sort of ask. One trick about meso. We may use the trick more here. This is a mirror plane. That means this side is mirroring that side, right? That's what mirror plane means. If that's meso, if that's R, that should be S. Because if that's being mirrored by that, what's the mirror of R? S. Okay? Let's do this real quick. Bromine's 1. Carbon with bromine would be 2. Carbon with carbon would be 3. H is in the back, that's R. Top one's R. If that's indeed a mirror plane, I'll bet you $100 gazillion at the bottom is S. Because the mirror of R is S. 1, carbon with bromine 2, other carbon 3, counterclockwise, H is in the back, S. See, in meso, you'll have R on one side, S on the other. If it's mirroring, if each side is mirroring each other, shouldn't you have R and S? That's another way to help maybe. For example, over here. What's here? Is that a plane of symmetry? I mean, carbon with chlorine mirroring carbon with chlorine, methyl mirroring methyl. I would do a fissure, much easier to see the fissure. Or I would do the trick I just told you right here. RS, right here. 1, carbon with chlorine 2, carbon with other things 3, H here is in the back, so that is what? That's S. Okay? Does everybody agree that this carbon over here is the same? It's got a methyl and a chlorine also. There's potential for this to be a mirror. This side mirroring this side. It's only a mirror though if that's R. What is this? Chlorine's 1, carbon with chlorine 2, methyl 3. H here is 4, so it's 1, 2, 3. That's counter. So it's R. So we got one side R, one side S, and they're otherwise identical. I mean, so do they seem like they're mirroring? Yeah. They're mirroring each other. They're the same thing, and one is R and one is S, so they're mirroring. So, what's the answer here? Meso. One side's mirroring the other side, i.e., there's a mirror plane. Now that's the trick way to do it. Let's do it by putting it in a Fisher projection. Let's call this chlorine 1, that chlorine 4. Let's call this the ground. Over here, is chlorine 1 going back? What side is that methyl there on? Chlorine 1 going back, methyl's on the right. That means the undrawn H is over here. Okay, here's the ground. Keep feet on the ground. With the chlorine 4 going back, the methyl is on my right. With chlorine going back, methyl's on the right. H is over here. Lo and behold, now we can easily see the mirror plane. It's much easier when you draw it in a Fisher. Right? We already knew that because we knew one. If this is mirroring this, whatever that configuration is, such as R, the other one has to be S. How about this guy? It's the same. It has the same connectivity. Is it going to be chiral or not? Chlorine's 1, carbon chlorine 2, methyl 3, H in the back. So this is R. Chlorine 1, carbon with chlorine 2, methyl 3, H in the back. This is R. They're both R. So is that a mirror plane? No. The mirror of R is not R, so that's not a mirror plane. Now we need to move on, but if you drew that in a Fisher, you would see, once you get it drawn, you would see that you can't draw a mirror plane. Okay, so I showed you the little trick. How about this guy over here? What's that, S? Yep. Are they both S? Yep. I think they're both S. Are they? So since they're both S, is it chiral or achiral? It's chiral. There's no mirror plane, because if there's a mirror plane, it has to be SR. Get the trick? If there's an internal mirror plane, you've got chiral on both sides, they have to have different configurations if they're mirroring. But again, you can always put them in a Fisher. You need to practice your Fisher. Okay, let's look at these here. Okay, this takes us all the way back to reactions and seeing what the stereochemical outcome is. Methyl here. You got this alkene, BH3. What are we doing to the alkene with these conditions? Hydroboration oxidation. What it turns the alkene into what? Alcohol with non-Markovnikov orientation, if we think about that. So if we draw this product with no stereochemistry, we will have what now on this carbon?
Hydrogen.
A hydrogen, what will we have here?
OH.
OH. Okay, there's a new H there. So we're adding water across the double bond. Anti-Markovnikov. There's lots of mechanistic thought there, right? Alkene attacks boron. Where would cation form? Would cation form on left or right?
Doesn't form.
Right.
Right,
Also
it's
doesn't
anti-Markovnikov.
No, we would start on the left and we'd end up on the right.
Form on the left. That's more substituted. But does it really form?
No.
No, because the boron throws an H at it. Okay? Mechanistically, this attacks BH3. We can get, again, I don't think I'm going to do stereochemistry here yet. BH3, so we got H, 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 that's now minus. Phenyl 1, that's a cation. Is this really formed? No. What happens? Hydride shift. So we got BH2, and we got an H here. And then what does the magic step do? Replaces this with OH. That's what I got drawn there, right? Now let's think about stereochemistry. The new B or the B and the H here, are they on the same side or opposite sides when they're added? Same side. Same side. So we need to show a side. Really, we need to maintain the stereochemistry here. So at this point, what I would do is, I showed you this early on. Let's do this fresh, but let's start with maintaining the stereochemistry by turning this. I'm going to turn it, instead of like this, pretend these are going up here. I'm going to turn it like that, so these are going back. And this thing is coming forward. I'm just going to turn it. Put the methyl back, phenyl 2 back, put the phenyl 1 forward. So all I did was turn that. And so now it's like, instead of like this, kind of like this. You have to imagine that. Now we can come in from this straight up or straight down. This alkene can attack the boron and it throws the H back and both bonds would be down. And so what I would do is I would get rid of this and put both bonds straight down. BH2 straight down, H straight down. And so that's your mechanistic thought. This is a syn hydroboration. But this can also add from the top. And so we would have a double bond like this. If it came from the top, you'd have a BH2 straight up and an H straight up. You get both of these. Because it's 50-50 of coming in from bottom or top. Now we know the magic step just replaces this with OH. Here are your two products, shown with the stereochemistry maintained. Now the question asks you to draw these in Fischer projection and tell if they are erythro or 3O. But it also tells you to put phenyl 1 at top and phenyl 2 at bottom. Oh, we lost phenyl 2 here, right? Phenyl 1 at top, phenyl 2 at bottom. Phenyl 2 at bottom, so this is the ground. I'll do this one here.
Can you just twist it in that drawing?
I'm going to look at it like I've done before. I'm going to put my feet on the ground, and I'm going to look at it through here. The H is in the plane. With the H going away from me, what's on my right on this carbon? Phenyl. It's bold. It means it's coming off the board towards you. If I'm laying here on the sofa, feet on the ground, H going away, phenyl is coming towards you. H going away, phenyl is on right. That means the methyl is over here. That's a methyl. Now, I just want to bend my knees and put my head here. Keep my feet on the ground, though. Feet on the ground. With the OH going away, the phenyl is on which side? It's going back behind the wall. So if the OH is there and the phenyl's behind the wall, that's on my left. So with the OH going away, the phenyl's on the left. What's on the right? What's undrawn on that carbon? It's an undrawn H there. An undrawn H would be drawn bold. It's to the right with the OH going away. There you go. That's inefficient. But you were asked to draw phenyl 1 at top, phenyl 2 at bottom. So what can we do here? Just turn this up and turn this down. And if we redraw that, phenyl 1 at top, H here. Methyl swings over here. Phenyl 2 at bottom. Let's just turn. OH comes here. That goes over here. There you go. With phenyl 1 at top and bottom, erythro or 3O? High priority groups are on the same side. That's not Z. That's EZ nomenclature. This is erythro E. Erythro. This is erythro. What would this be? You need to do this one also. This is also erythro. If you do it, it will also be erythro. What will be the difference? They'll both be on the other side. It will thus be what? These will be enantiomers. These will be enantiomers of each other. So let's look at some terminology. This reaction gives enantiomers. That's what we just stated. Is this reaction enantioselective? No. Does it only give one enantiomer over the other? No. So it's not enantioselective. Here's a take-home. None of the reactions we've done have ever been enantioselective. Can't be. This reaction cannot be. Here's why. It has to do with optical activity. Optical activity cannot be just created from nothing. Is this optically active? No. No. To be optically active, it has to be chiral. That's not a chiral molecule. This is not optically active. Nothing here is optically active in the starting materials, so nothing there can be. You cannot make something not optically active. Is what we made optically active? The entire mix. Why is the entire mix not? Because it's racemic. If you do this reaction and only get this one, what do you want to call these two enantiomers? Like a DL pair? If you do this and only get D, I don't know what this is. That means it would be optically active, and you would get a Nobel Prize. You cannot create optical activity from nothing. That's sort of the take home. The other reason is you get both because the reagent can attack from the top or the bottom 50-50, and it gives both of these. And if you do it, you're enantiomers. Okay? Gives only erythro. For example, not 3O. Did we get any 3O here?
No.
No. So what's this relationship?
Diastereomers.
Diastereomers. So is this reaction diastereoselective?
Yes.
This reaction is said to be diastereoselective because it only gives erythro, not 3O. These are diastereomers. I mean, I could draw you a 3O version of that, but this reaction doesn't give it. So it's diastereoselective. But it's not enantioselective because you get both enantiomers. That's that type of terminology, and that's described on the yellow sheet sort of here. Okay? Please try to work whatever we're on that warm-up that we did not do today. We'll see if there's any questions on Thursday. We need to move on to alkynes. Okay. Test is Tuesday, week from today. Yeah. Yeah, alkynes will be on the test. It shows a summary of our alkyne reactions. The alkyne reactions are going to be quite similar to the alkene reactions. It's going to be a pi bond reacting with the same reagents that we've already been using. HBr, bromine, BH3, maybe aqueous acid. The only difference, guys, is that alkyne has 2 pi bonds and an alkene only had 1. It's really twice the fun. Okay? But let's see the similarities, okay? It's not going to be all brand new stuff. Here's an overview. Let's first quickly look at some nomenclature. 2 types of alkynes, terminal versus internal. We mentioned these during the IR lecture. So the alkyne is on the end, and thus there's an H on the alkyne carbon. That's called a what? Terminal alkyne. Terminal alkyne has the SPCH. This would be called a what? Internal. There's no SPCH. Okay? That's just some terminology. Let's name this alkyne on the end. First off, you see the main functional group is alkyne, so it's named with an "-ine" ending, Y-N-E. Alkene, hexene. What's the longest continuous chain here? 1, 2, 3, 4, 5, 6, 7. That's 2 carbons because that's linear through there. 1, 2, 3, 4, 5, 6, 7. So we have, what is our prefix? 7. Yep. Time. But we have to say where the "-ine" is, where the triple bond is, just like with alkenes. 1, 2, 3. 3 heptyne. You would start on the right because that would give your triple bond placement at the lowest number. Does that look pretty consistent with what we did with alkenes? It's 3 heptyne. What is this guy over here? One pentyne. Everybody agree? Yep. The alkyne is at the 1 carbon. 1, 2. You just list the first number, just like your alkene nomenclature. Question?
Why is the hydrogen drawn for the terminal one? Like,
It doesn't have to be. Just drew it just to really clarify it. I reckon if I drew it just naturally, I'd probably want to put it there. Also with my aldehydes, I just like to put the H of an aldehyde there. I'll probably just do that just naturally. If it's not there, it looks a little odd to me, but you don't have to put it. Of course, if it was not drawn, you would say, hey, that carbon does have an H on the end.
right.
Okay? I mean, you'll see it a good bit, just drawn like that. Okay? But that's, there's an H there. Okay? So the carbon has 3 bonds, it's an alkyne. Okay. Let's look at electrophilic additions. HCl. Hey, look at there. Magic eraser. Need to keep that one. Okay, HCl. High bond reacts. What's our electrophile here? H plus. H plus, Cl minus. Source of H plus. High bond attacks. Are we going to leave cation on right or left? Which carbon of the alkyne? It'll be on the left. So new H on the end, there was already one there. This here is a plus. It's very analogous to our alkyne reaction. We just got a pi bond left because we only used one of the pi bonds that we started with. So that hinged away when it made bond to H, leaving that carbon as a plus. Now originally it's sp linear. It's actually still linear. What's the hybridization of that? It's actually still sp. It's actually still linear. For some reason I drew it like that because I know I'm coming towards a double bond. Is this actually formed or does something back bond? That doesn't have a lone pair. That's actually formed. What then happens? What adds here? Boom. And there you go. There's your first product. But that's really nothing new, is it? But guess what? We just made an alkene. Can alkenes react with HCl? Yeah. It's twice the fun. This just reacts again. Where are we going to put cation? Left or right? It's actually left, and there's 2 reasons. First, because of this donation, but we get this. UH there, there's 2 others there. Chlorine here, plus here. This donation here, this donation here, that's the best cation. There would be primary, this is secondary, that's best. What's another reason this is good? The other reason is actually more important. You would think that this chlorine hurts this. It actually helps it because these electrons can sort of move in here. This is almost could be considered back bonding, but it's not. What are we going to call this? What does that arrow movement give? Double bond to chlorine. Chlorine now has 2 lone pairs and plus charge. What are these? Those are resonance structures. So we get a resonance stabilized cation. That's the second reason, and it's actually the major reason of why this is best. The charge is delocalized. The charge does not just sit right here, but it's spread out onto the other chlorine. The true structure is somewhere in between. The true structure is a blend or a hybrid. It has some positive on the carbon, some positive on the chlorine. You need to know that there's resonance here. Ultimately, this goes back to p orbital overlap. This is sp2 with an empty p orbital. One of these lone pairs is in a p orbital, right? Because anytime a lone pair is next to a p orbital, it's going to want to be in a p orbital. Really what you have here is p orbital overlap. We're sort of showing that here. Ultimately, the other chlorine that's sitting here does bond here. You can always work with any resonance structure. You could bond it here. If you wanted to bond it here, you have to push these up. Either way gives this. And so you end up with 2 chlorines on this carbon. That's called a geminal dihalide. Geminal meaning twins. It's like there's twins on that carbon. Before we made vicinal dihalide, what does vicinal mean? Vicinal, they were adjacent, like they were in the same vicinity, but they were not geminal. Question?
So when we draw the mechanism, do we have to show the potential resonance structures?
Depends what the question says. If the question says show all resonance structures, then you would need to be able to show it. You need to understand resonance. Again, we will see resonance multiple times. And then when we get to test 3, we'll cover resonance. Okay? But we can't avoid it. This is resonance. Okay? Question?
Could we say that that medium one, put in the middle one with just the one chlorine, would that be a major product? Or would you be assuming that it follows through both reactions at the time?
Question. Question is, can you stop here? It's actually pretty difficult to stop here. And quite often you just react this with HCl to equivalents and you just go all the way. It's kind of hard to stop in the intermediate.
So you wouldn't call that a major product if you were asked?
Major product?
Yeah, like if you were asked to show all the major products of that reaction, you would not show that intermediate.
If this was just one equivalent, then that would be a major product. To get the end product, you need 2 equivalents. It's hard to stop at just one, so usually you do this, you just add 2 or excess, pushing it all the way to the end. It's hard to stop it here. Okay, down below, let me take this through a little bit before we dismiss. You can look at that. Again, down there we're doing elemental halogen, should be straightforward. Why is this E and not Z? Well, that's because how does bromine add to an alkene? Anti or trans, it's going to be the same thing, you just don't have a double bond there. And at this point, double bonds react again and you end up with 4 bromines there. Question?
It'd be the same as instead of the RT, you're adding CL2. You would also have
Right. Chlorine would give the same outcome. On Thursday we'll look at one of the hydration reaction. Reacting an alkyne with like H3O+. Hydrate the alkyne. We will see a little change here. You'll hydrate once to get an enol. This will not hydrate again. Instead, it will undergo a rearrangement called a tautomerization. Please be doing some reading about tautomerization and looking at the other topics on this page and the next page. We'll also do reduction of alkynes. Okay? Everything we're covering for alkynes is on these handouts. Other things in the alkyne chapter we're not covering. We'll complete the alkyne stuff on Thursday, and we'll talk then about the test on next Tuesday. Anything left, guys? I forgot to tell you, you're just going to be in a classroom. The Wednesday and Thursday night will be in 1004. I think it's next door. Thursday during the day, you'll be in this room. So meet at your lab time in those rooms. And you'll turn in your polarimetry when you go to that lab. Friday's group will have to attend 81. Again, this week is all optional, but I would highly recommend you attend.
You just turn in my light on.